Hello, everyone. My name is Ashraf Qasim, and I'm with the Singapore University of Technology and Design. And it's my great pleasure to introduce Professor David Andrew Patterson, Professor of Computer Science and Emeritus at the University of California, Berkeley, which he joined after graduating from UCLA. Uh, Professor Patterson is a distinguished engineer at Google, Vice Chair of the Board of Directors of RISC-V Foundation, and Director of the RISC-V International Open Source Lab, or Rios Lab. David has made many significant and pioneering contributions to computer systems and architecture, among the most significant being the Reduced Instruction Set Computer, or RISC, Redundant Array of Inexpensive Disks, RAID, Network of Workstations Now, and many, many more. Without further ado, it's my distinct pleasure and honor to invite Professor David Andrew Patterson to begin his talk. David, please.
Well, thanks for the kind introduction. Go ahead and get started. Okay. And so I'm going to tell you the history of reduced instruction set computers or RISC, and then what's going on today in very exciting times. So what is an instruction set architecture? When software talks to hardware, it has a vocabulary, and the words of that vocabulary are called instructions. The vocabulary itself is called instruction set architecture. That's a lot of words because we often abbreviate ISA or even pronounce it as ISA. But it's the vocabulary of the hardware, and it's the most important interface since it determines the software that can run on that hardware. And software is distributed in these instructions, so that's what determines it can run on it. So a computer is kind of like a calculator. If a computer has a keyboard for input and a display for output, like a calculator does. A computer has instructions: add, subtract, multiply, and divide, just like the keys on the keyboard. Those kind of commands work. And then the computer also has instructions that you can save numbers in memory and you can call them later. Those are called load and store instructions. And what a program is simply this recipe of thousands to millions of these really simple instructions, but executing incredibly fast at billions of instructions per second. And if you do that, you can get a pretty smart computer. So these low-level instructions, it was pretty tedious for programmers to write them. That's referred to as machine language. So pretty early in computing history, we invented what are called high-level programming languages and programs to translate them called compilers, so that you could write and debug something more easily, and then the translators would turn it into something that the computer can understand. So examples of these programming languages in the past, programming languages like BASIC, or more recently Python. So it'll let you write something like on this next slide is B divided by C plus D goes to E, and the translator would turn that one line of high-level language into the following instructions: load B, load C, do a divide, load D, add, and store. So that gives you a flavor and remind you a flavor of what's going on. Now, and then this typically is true, the high-level language, often one line that would turn into 5 or 10 of these machine language instructions. All right, with that little reminder about instruction sets and what they look like, let's go back 50-some years, and IBM had 4 different vocabularies. They had each of these lines of computers had a different vocabulary. They had their own input-output system. It had its own software stack, and they were targeted at different market niches. So IBM had this radical idea that we could unite these 4 different incompatible lines around a single instruction set, one instruction set architecture called the IBM System 360. Now, then and now, the hard part of designing computers is what's called the data path. That's kind of the thing, the brawn of the computer, the thing that crunches the numbers, that does the adds, subtracts, multiplies, and divides. That's the data path. The hard part is the control, which tells the data path what to do. So Maurice Wilkes, who was the second person to win the Turing Award, he invented this simplified way of doing control. He said at the time, logic was more expensive than read-only memory or alterable memory. And read-only memory was faster and cheaper than RAM, so his idea was to use read-only memory to kind of program it as if you could program a computer, and that's how you'd specify control. He called that microprogramming. So IBM needed a way to do control across these widely varying sizes of machines, so they bet on Wilks's idea of microprogramming. So in April of 1964, IBM made the biggest announcement in its company, and here's an example of 4 different models of IBM computers. You see they varied from 8-bit computers all the way to 60-bit computers. The clock speeds were different speeds, the memory speeds were different, and the cost was very different. It varied by a factor of 5, and in today's dollars, it'd be from $1.5 million to almost $9 million. So IBM bet the company that they could have a single instruction set, so they run the same software on all these different types of machines, and IBM won that bet. That was became incredibly successful in the 1960s. Whoops, let me go back. Okay, and I point out Fred Brooks, who is also one of the Turing Award winners, and he won the Turing Award in large part because of his contributions to the IBM 360 instruction set. Okay, so that was what's called mainframe computers from IBM. Next became integrated circuit technology. So in the mainframe era, there's a mix of technologies, but in the integrated circuit era, the logic, RAM, and ROM were all implemented using the same transistors. There was not much difference in speed between the alternate memory and the read-only memory, about the same speed. And with Moore's law, you had a lot more memory. So the size of the microprogram could grow. And since it was alterable, it was easy to fix bugs in the microcode. So what that enabled was much more complicated vocabularies, much more complicated instruction set architectures, which I refer to as complex instruction set computers. And a classic example of that time, what was called a mini computer, and it had the VAX instruction set architecture. And it had the microprograms were very big because it's a very complicated instruction set. Okay. So next comes the microprocessor. Moore's law continues, and we finally, in the early 1970s, there's enough transistors in integrated circuit to build a home processor. So these were experts in semiconductors and designing chips, but not so expert in microprocessor or computer architecture design. They weren't that good about designing these vocabularies. So they basically imitated what the mini computer people at DEC or the mainframe computers at IBM did. Their expertise is in building chips. So the way they competed with these microprocessors is that they would add instructions, which was pretty easy with the microcoded control to be able to do that, and they would justify them with writing, machine language programs like I showed you before. They'd say, this instruction would be very helpful in the situation. So Gordon Moore, the inventor of Moore's law, had this insight in the 1970s that whatever was, they had an existing instruction set architecture, and his insight was the next one they did was going to last for the lifetime of the company. So he hired a lot of PhDs in computer science, sent them up to Oregon here in the United States, north of California, and their job was to invent Intel's next great instruction set. And it was a very ambitious project, started in the mid-70s. It was going to be where microprocessors at the time were 8-bit and approaching 16-bit. They were going to be 32 bits and a very sophisticated architecture. It had what's called capability-based addressing, so they put security into it. It had its own unique operating system written in the esoteric language called Ada. It's a very ambitious design. Unfortunately, it was kind of more powerful than the technology, so they had severe performance problems, even though it was ideally a single chip processor. They couldn't fit in one chip, so it was multiple chips, and usability problems. So it was actually delayed. They were hoping to have it done in 1977 or maybe 78, so it was delayed, and so they had to tell Gordon Moore it wasn't going to be ready till 1981. So Intel was in trouble. They needed a 16-bit microprocessor, So they started a 52-week project to do everything to get, because it was an emergency, to go from 0 to an instruction set architecture, some software, and a chip that they could sell in just 52 weeks. So that left them only 3 weeks to design the vocabulary, design the instruction set. So they made it assembly language compatible, as it's called, with the older 8080, because they had a very short amount of time to do that. So it was announced, and it wasn't that exciting when it was announced. It was done quickly. It was Intel's entering the market, but to their great fortune, IBM was coming into the personal computer market, competing with Apple's computers, and they announced the IBM PC in 1981, and they selected that vocabulary for their use in the IBM PC. The Motorola 68000 had a much more elegant instruction set architecture, but it was late and they needed to go ahead, so they picked Intel. That was a huge boon because at the time they thought maybe they would sell 250,000 PCs, and that would have been nice for Intel. That would have been successful, but IBM was wrong. They didn't sell 250,000. They sold 100 million. So they underestimated by a factor of 4,000. So suddenly the 886 vocabulary became tremendously valuable because the software was distributed in its instructions, and Intel owned that instruction set. It's called binary compatibility. So overnight, the 52-week crash project became the future of the company, and that future was very bright because of the importance of PC software. All right, and let's start looking at these microcoded instruction set architectures. So there was a change in the community where the hardware-software interface was risen from programming in machine language or assembly language into these high-level languages. It was done all the time. Even operating systems could be done with it. So now the translators are what mattered. The compilers mattered, and what mattered was the output of the compiler. So John Koch led a group at IBM. John Koch is also a Turing Award winner. And he worked on a simple, what we call pipeline computer. It was a mini computer like the VAX one, and very advanced compiler technology. So they had their own computer that they were building, which we would call a RISC computer today. But they decided to try their compiler technology out on that IBM mainframe computer. But they only used the simple instructions from it, register, load, store instructions. And what happened? Well, some programs ran 3 times faster than if they had used the full instruction set. So that's surprising. So subsetting the instruction set led to speed. And then some researchers at the mini computer company used equipment in the 1980s found that of this large 5,000 lines of microcode, that it wasn't as efficient as they thought. They thought the average number of clock cycles per instruction would be 5, but as they measured it, they found that was wrong. It was 10. And they found that 20% of those instructions were 60% of the microcode, but hardly used at all. So rarely used, even though it was most of the complexity of the instruction code. So now we talk about making the transition from complex instruction set to reduced instruction set. So instead of a read-only memory with microcode or a RAM memory with microcode, we turned it into an instruction cache of user-reversible instructions. So it would be alterable there instead of having an interpreter that does it. And so this meant, because it's a cache, that memory could contain what's the program that's running rather than this interpreter. So that would be a big advantage. It's a pretty simple instruction set architecture to do RISC. It's kind of like as simple as micro instructions, just not as wide. They're 32 bits wide, not 96 bits wide, but that's simple because that made it much easier to do pipeline implementation, so you could run much faster. And by the way, as we saw, the compiled programs didn't use very many of those CISC instructions anyways, so you weren't giving up a lot. And then there was people at IBM came up with an algorithmic breakthrough that made it a lot easier to use the registers that are inherent in RISC, that made it much easier and more efficient to compile these programs to use it. And this is where Berkeley and Stanford enter into the scene. This is a picture, that's me in the middle with the glasses there in the front row. And this was students in a class. We taught a class to teach about microprocessor design and explore the ideas of instructional computer. And so this first one is called RISC-1. It was done through a series of classes. It had only 45,000 transistors. This was followed the following year. Two of the students decided they could do, after RISC-1, they worked on RISC-2, and they made a much more efficient design. They needed fewer transistors, but it ran much faster, and it was a much more elegant design. And then my friend John Hennessy, that's when he got into it, and he did his design. It's called MIPS, and it contained even fewer transistors, but it was also an excellent microprocessor design, and it was done with grad students there at Stanford University. And I can still remember when these two chips were presented at the main integrated circuit conference, that it was a remarkable moment in time when grad students at Berkeley and grad students at Stanford, each of them could design a microprocessor, design and build a microprocessor that was arguably better than what industry could build. Now, that's not to say that RISC was accepted widely. It was very controversial. So when we talked about the ideas of RISC versus CISC, we wrote a paper, and then these people at Digital Equipment Corporation, Doug Clark and Bill Strecker, wrote a rebuttal, basically. And I quoted that rebuttal. This was in 1980 when we were just getting started. The superiority of RISC over a corresponding CISC will be very difficult to prove. Surely a simple instruction set can be implemented in less silicon area than a complex one, but that doesn't mean that the system cost effectiveness increased by reducing instruction set complexity. So at the beginning, they said, well, this isn't clear, this is controversial. It's not obvious how it's going to turn out, which I think was a very, that's a very reasonable thing to say when we started in 1980. But it was still controversial 5 years later. Here's quoting from an article that appeared in a computer magazine in 5 years, and the quote was, "The avalanche of publicity received by RISC has swept away objectivity. Articles of RISC research are simplified, overstated, and misleading." So those are pretty strong words for a published paper, and the draft of that paper was even more pointed. So this helps explain this formula. It took us, we didn't realize in the beginning how to explain these advantages for RISC versus CISC, but this formula helped us. And what we can do is, how fast a program runs is how long it takes the time per program. Well, we could separate that into three factors. How many instructions it takes to run the program. So this is the words of the vocabulary. Those instructions like load, store, add, subtract. How many of those does it take to run the program? Okay, that's one factor. Then we use a clock to be able to control the computer. So what's the average number of clock cycles per instruction? And then it's the time per clock cycle, last factor. So when you see like a 2 gigahertz clock today, that's a 500 picosecond time. So it's the number of instructions per program times the average number of clock cycles times the time. Well, that's the three factors. And what the insight was that the CISC executes fewer instructions per program, maybe 3/4 as many in that first article, but a lot more clock cycles per instruction. So the first term is smaller, but the second term is much bigger. So RISC executes on average maybe 4 times faster than CISC. And eventually Doug Clark, to his credit, and another colleague, that was 6 years after that, 11 years after he got started in 1991, they wrote this paper that said, yeah, it looks like RISC is 4 times better. But this notion, of making computer architecture more quantitative led John and I to try and write a book that captured those ideas. Oops. Let me go back. Sorry. And that's the cover of the book. So that book came out in 1980. That's what Professor Ashraf talked about. Maybe he has a copy of that book. That's what the first edition, that's now in the 6th edition. And basically, Hennessy and I shared the Turing Award in part for the RISC ideas, in part also for this book, as it put computer architecture on a much more quantitative foundation than it was in the past. So this resolution, well, John Hennessy led a startup with the name of MIPS, and I consulted at Sun Microsystems on the Spark instruction set. They were successful in the marketplace in the 1980s. The paper that came out by the people from DEC also announced it. Now, Intel didn't just take this line down, although RISC seemed to have technical advantages. They had this instruction set architecture that had all of the software for the PCs, which was a very valuable software base. And their semiconductor technology was years ahead of everybody else, at least 2 years ahead of everybody else. So to their credit, in 1995, their Intel microprocessors actually put a translator into hardware that, while it was executing, would translate from CISC instructions to RISC instructions. So they could do that, and then any of the good ideas that the RISC people had to go faster, they could take advantage of. So they had to pay that extra overhead for that translation, but their semiconductor technology was a couple of years ahead of everybody else, so they could hide it. So Intel ended up with this trick dominating the PC era, and they're still very powerful in the cloud today. But what's happened is most of the microprocessors in the world are in the edge or in your cell phone, in your iPads, and so RISC dominates the post-PC era, and that's why, as I said in the introduction, 99% of the processors today use RISC ideas. And I think this slide just says the same thing. They got up to 350 million per year at the peak of the PC industry, but the cloud era, one of the things that's different is instead of buying a microprocessor, there's something called a system on a chip. So it's a chip that integrates lots of designs, which are called intellectual property and single chip. So you're deciding what to put in your system on a chip rather than buying microprocessors. And especially for cell phones and iPads and things like that, or Internet of Things devices, it's really important for the die size to be small and to be very energy efficient. So paying that extra translation step was difficult to afford. And there's more than 20 billion chips per year now, and 99% of the risk. Okay, just a quick refresher. I use the word cloud and edge. The cloud, although it's kind of a mystical name, that's simply remote computing and storage and distributed data centers connected via the internet. And the edge are just these tiny computers, often battery powered, also on the internet, and that's where Internet of Things. But that's what we think the future of computing is at the extremes. The exciting parts are the cloud and the edge. Personal computers aren't an exciting vision of the future. So thus far, instruction set architectures have been proprietary. Somebody owned them. So the two most popular ones are the Intel instruction set architecture, which I was just talking about, and ARM. ARM has a very popular instruction set architecture, and those two dominate the world today. Now, one downside of proprietary instruction sets is their fortunes are associated with a company, and so proprietary instruction sets can be bought and sold. So MIPS is on its 7th owner in its kind of 35 years it's been around. And you may have seen the news recently is that ARM is being purchased by NVIDIA right now, and that'll be the 4th owner. So when that happens in the commercial world, this can be upsetting to people because people are a little worried who's going to own the instruction set architecture for Unity. So this led to a new idea, which is open instruction set architectures. 10 years ago at UC Berkeley, we needed to have an instruction set architecture. We had a research project, it was even funded by Intel, but we couldn't use Intel. That was a proprietary instruction set. Intel wanted to control it, and they didn't want anybody using that instruction set, even research labs that they sponsored. And similarly, ARM wanted to protect what they're doing. And also they were very complicated. So we decided to 20, 30 years after the RISC architectures of the 1980s to do a brand new version, learning from the mistakes of the past. And since we had 4 versions of RISC in the 1980s at Berkeley, they named it RISC-V in honor of those other efforts. So let me tell you about RISC-V and how it's different and why it's a different architecture, which is there's both technical reasons and business reasons. The first is the business reason that it's free and open. That means anyone can use it anywhere in the world. And so what I think this is going to mean is a lot more competition, because there's many more people building RISC-V processors, not just one. And I think more competition means going to be more innovation. And again, from a business model perspective, it's a really big deal for companies, especially small companies. Normally what you'd have to do if you pick a proprietary instruction set is negotiate a deal with the owner of that instruction set, and that will take time to negotiate the deal, because what royalty rate you're going to pay and what are you going to pay up front. And it'll cost money, of course. With an open architecture like RISC-V, you can just pick the architecture, get started, and later figure out who's going to supply it. RISC-V is a simple and elegant core design. So why is that? It's because it came from a university. We were designing an instruction set for us to use in our classes. And whenever you do try and teach a real instruction set, you use a small subset to explain it. Like that happened in Hennessy's My Textbooks. We would take maybe 40 or 50 instructions, and that's the essence of that instruction set, and that's what we would teach. Well, RISC-V fully embraced that. 47 instructions are what are called the core instruction set architecture, and all software runs on it. And so that's by definition, this simple core will run the full software stack. It's not just for education. It's not simply for education. It's helpful for education, but that fulfilled our goals as part of doing it. So if that core is all you need, then what about other instruction sets that you need? Like if you want to do floating point, or if you want to do encryption, or if you want to do maybe machine learning or something like that. So the way that's handled in the RISC instruction set, which is a new idea, just like there's a base that all software runs, a new idea, is to be optional modular instruction sets. In the past, with proprietary instruction sets, they grew bigger and bigger over time. And so if at the Intel architecture, which came out in 1978, if in 1980 they added instructions, everything after would have them, and so forth. Every few years, if they added instructions, everything into the future. So it's kind of like in middle age, people get bigger, way more. That's what happened with instruction sets. That's not the case for RISC-V. It's got this skinny, slender core, and then there are extensions that you can use or leave out. So if you don't care about machine learning, you don't have to add those instructions. If you're not going to do floating point computations, you don't have to add them. So that's a new idea, that it's modular as well as simple. And when we did this, we knew that Moore's law was slowing down. And so one of the ways we were going to make computers go faster was to be able to add instructions for special applications. And so it's designed to be easy to enhance. So we left space aside to make it very easy to add instructions. The older instruction set architectures, that wasn't important for them. They didn't expect people adding instructions, so it's harder to enhance them. So there's room to evolve. So I'd say the big idea is it's free and open, and then these three features of the actual vocabulary really make it stand out. It's simple and elegant, it's modular, and it's easy to enhance. Now, like most, it was clear 10 years ago that the future was going to be the cloud and Internet of Things. That was obvious then, so we designed for that. So it's designed to work both from the tiny and large computers. From a computer architecture perspective, that turns into how many bits of addressing is. So the tiny computers have typically no more than 32 bits of addresses. The big computers have 64-bit. RISC-V is even planning for a future. We've designed a 128-bit version. We won't need that for many years, but one of the hardest things to do in computer architecture is when you run out of address bits, and some number of years from now, 64 bits won't be enough, and we're already ready for that. Now, if it's an academic instruction set is what happens after the grad students graduate, or what happens if professors get bored and want to do something else. So you can't base an industry on something that's kind of ephemeral, like faculty interest. So we set up a foundation similar to what the Linux Foundation did, so that the community can own and evolve the instruction set. So the name of that organization is RISC-V International, and this foundation owns it. So there won't be companies going in and out of business. There's many companies involved in RISC-V International. And then a final feature that's in this modern world is the importance of the openness, is people want to know what's in the hardware design. So many nations around the world want to know what's inside the computers that they're going to be using. And so by having an open architecture, you can design it yourself. And there's also this idea of having an open architecture, open in vocabulary, means there can be open implementations that people can share. So open source implementations of that architecture, so you can see what's inside the chip that you're going to use if you want to do that. So these are the big differences about RISC-V. The business reason, free and open. It's got some cool features that are different from other ones. Like others, it's designing for small and large. Because it's open, there's a community around it, and in this modern world, people want to know they don't want any surprises in their hardware, and this openness helps with that. It's really a worldwide phenomenon. There's more than 600 members in 50 companies all around the world. It's very popular in Europe. It's very popular in the Asia Pacific and very popular in North America. In fact, probably about 1/3 of the members are in each of those regions. Now, to try and capture kind of the enthusiasm about RISC-V, we put together a video to celebrate the 10th anniversary. We're going to have a party, but because of quarantine.
RISC-V needs a theme song. You know, something like "We Built This City" or something that has that energy, because that's what I feel. I see passion and dedication and an emotional attachment to RISC-V throughout our community that is so energizing. That for those who haven't joined the community yet, come on in. It's a really, really powerful place to be.
I mean, I'm actually quite impressed. I think the kind of energy that is going into it and the way you have brought so many parties together is absolutely marvelous.
All computers run programs at the very lowest level. They need to have a common lingua franca. If there is a lingua franca, then we can start building standard computers. Computers are getting themselves embedded into every aspect of our life. And for that, you need computers that are open so that people can standardize on something. And RISC-V, with its open ISA, is the only option that is available if computing is to become all-pervasive. You can't build a society on proprietary foundations.
The key differentiator for RISC-V from other processors is the openness, the fact that you don't need to sign any agreement whatsoever to just start using it. With this, you can just download it. You don't have to ask anyone's permission, and that is a fantastic difference.
Now that I'm doing architecture, I use RISC-V, and I get so many things for free. I can focus on adding value on a few instructions and leverage tens of millions, hundreds of millions of dollars invested over the last 10 years and go that much further by being able to leverage that infrastructure.
We had a workshop where we announced that we are going to put RISC-V in every GPU and every chip that we have.
Starting this year, 95% of resources are put in RISC-V development.
When Western Digital announced we were going to transition 1 billion cores, I essentially tried to replicate that momentum that IBM's $1 billion investment did to Linux with RISC-V.
Today, RISC-V is a movement that can no longer be stopped. The conversation started to change to why not use RISC-V as opposed to the early years where it was like, why the hell would I use something other than what I've always been using?
RISC-V is the Linux of the processor architecture world. It's the transformation to an open source platform that allows many, many more innovators and inventors to contribute to the advance of the technology.
I think of ARM as a company that has paved the way for RISC-V. It was always destined to act as a place filler in the history of computing as a precursor to RISC-V.
There is an immense opportunity for RISC-V to be in 5 years the leading ISA for computing. I mean, it seems to be incredible, but doesn't look so impossible now.
Okay, so that was the 10-year video. If you're interested in that, there's longer videos than that. Now, RISC-V is behind these other architectures, so its ecosystem isn't as strong. So one of the things that we're doing is called the RISC-V International Open Source, or Rios Laboratory. It's a 5-year mission that's done jointly in China and Berkeley at something called the Tsinghua University and UC Berkeley Joint Venture. It's going to be trying to create intellectual property so that people can build open source cores around RISC-V, and it's funded by the Shenzhen municipality and matching companies. And we're going to be growing it. I'm going to be leading it, and one of my former students is going to be the co-director of the lab. And he's actually a graduate from both Tsinghua and UC Berkeley. To give us some focus, the first thing we're going to do is we need something to design what pieces we're going to build, and we're going to build a small board computer, kind of like a Raspberry Pi based on RISC-V, and we call it Pico Rio. It'll provide a roadmap. It'll also make it an inexpensive board so that people can develop software on it to help make RISC-V more popular. And we plan to license it out for people to use. We'll control that. And we will ship it sometime next year is what our plan is. And the vision for RISC-V is for it to be ubiquitous. You know, in 5 to 10 years, I think RISC-V will be everywhere, from not just IoT, but mainframes, data centers, cloud, everywhere. I think another thing that I'm hoping is because of this open source applied from software to also hardware for RISC-V, that'll let us find ways to collaborate across these boundaries to make it a more fully globalized industry. To me, the inspiration is the Flying Tigers. Before the US entered World War II, they had 400 men resign from the armed forces and joined the Chinese Air Force, and they flew these P-40 airplanes that had the mouse painted on them that became known as the Flying Tigers, and they helped China in the early days of war. So I think this is an example of international cooperation that inspires us. Oops. Now, let me wrap up. Remember that this instruction-set architecture is this vocabulary of all the hardware. It's the most important interface. RISC is this instruction-set architecture, reduced instruction. RISC-V, the big difference is the business model that anyone in the world can use it, and that enables open source implementations that people can share, and I hope will lead to collaboration. Now, Rios is actually Spanish for rivers, and then we picked that because the river's name symbolizes the collection of resources from many lands to create a strong force that can change a landscape, and we hope the Rios lab at TBSI will help develop these open blocks using people around the world to create these strong forces that can change the technology. And if you're interested in the Rios lab or the Pico Rio, let me know. But with that, I think I'm ready for questions.
Thank you, David, for that most exciting talk. I'm sure all our audience members are fired up, and I see questions streaming in, but I suppose we have very limited time for questions. So let me start off with some of them. I think most of us will see those questions, so I'll go through perhaps some of the interesting ones. Like the first one at hand is, with the technology evolving and the Moore's law coming into questions, what are your views on how this will impact the, advancement of technologies related to processor, computer, development and design?
Yeah, we've benefited from 50 years of Moore's law, which is amazing. An exponential growth for 50 years. Who would have ever thought that would have been possible? And so we've become dependent upon it, both as people in the field, programmers used to computers getting faster, memories getting bigger, and then the whole world used to the cost of computation and the cost of storage to go down at this, to improve exponentially. And it's coming to an end, so it's a shocking result. What this means, it's because people expect these continued advances. It's going to be a lot harder to do them. It'll probably come unevenly. The area that I worked in here at Google has been for machine learning or artificial intelligence. And right now, it looks like we can build special purpose computers to make machine learning or artificial intelligence improve at almost Moore's law's rate without Moore's law by innovation. So it's going to be the future's going to look different, and it's going to take a lot more innovation by lots of parts of the software stack and hardware stack than it did in the past to keep making improvements.
Thank you. And I suppose there were also some questions about the, the advent of quantum methodologies and technologies. So what are your thoughts or insights about how this will impact, the landscape?
Yes, because I talk about this slowing down Moore's law. That's a pretty common question. What about quantum computing? Because you read about it in newspapers all the time. So the thing that's hard to keep in mind is quantum computing is an open research question, is whether we can build it or not, and whether it's going to be practical. First of all, quantum computing is absolutely big machines, right? This is cooling down to 0 degrees Kelvin. You try and isolate it from vibrations. So it could only possibly use the data center. We're not going to have a quantum cell phone. So semiconductors are still going to remain important for a huge fraction of what computers are today. Secondly, it's off, and it may not be practical application until 2030. There's a couple of National Academy studies here, and they talked about it in that kind of time frame. So when I started going to PhD program, there were people in physics who were going to work on fusion reactors, like the sun. It could be a phenomenal invention if it works, but they're still working on fusion. That still hasn't worked in a while. So I don't know that quantum's that far off, but we're not going to have quantum computers possibly. We're going to have to figure out something else to do this decade in the data center, and then for cell phones, we'll need to find something else to make improved computers that we keep in our pockets.
Okay, that's interesting. And I think your point about what you're doing at Google and looking at machine learning and all that also fired up some questions. So I think one relates to how things like how the human brain works, for example, has influenced the evolution of processes. I suppose neural networks and all that are one sort of structures in that direction. So maybe you could share your thoughts on that.
Yeah, there's some computer architects who are working on brain things. I think what they're trying to do is imitate how the brain works, to understand how the brain works. But so far, there hasn't been much of how the brain works that's influenced the design of the hardware. On the other hand, in terms of software models, like machine learning, there's absolutely people who are studying how the brain works and coming up with ideas of how you would do something in software inspired by the ideas of how the brain works. So that's a place where there is direct carryover. I know at Google and other places, they have people who study neurology as well as study machine learning. So from a software side, software inspiration side, certainly makes sense. Not so much the hardware. But what happens, the software comes with some ideas, we try to make the hardware to make that software possible. So more targeting the inspiration for things inspired by the brain rather than the brain itself.
Oh, that's exciting. Now, there was also some question. I guess this is someone probably who works in spintronics or molecular electronics. Do you see that making an impact on the technologies ahead for processor design and so on?
I know there are people who are looking for successors to the standard transistor and semiconductors. My understanding is that is 5 or 10 years, at least 5 years away before it's working in production. Because semiconductors are amazing technology. Not only is the best way to design one computer, but if you can build it, you can make millions of copies of it reliably. So it's a very sophisticated technology. So to compete with semiconductors, you have to not only make something that's better, to make one copy, you have to be able to mass produce it economically. So it's a very stiff challenge to come up with. So it'll take a while to do. So my impression is that in the next 5 years or so, we're going to have to use the technology, the standard semiconductor technology, and innovate at other parts of the stack to keep delivering improved value.
Thank you so much. I think I've been signaled that we have limited time, so maybe I'll sort of distill the final question into one that maybe would excite our audience. let's say, David, you're now back to a 20-plus-year-old graduate student embarking on your PhD. What do you think are some of the hottest things that you think you'd be looking at and following up on as possible research topics for your PhD?
Yeah, so first of all, I think it's great you're getting a PhD. I think one of the things that's happening is lifespans are extending. I'm older than both of my grandfathers. I'm 73 now. They didn't make it that long. I think you should be expecting to live to be more than 100 if you're 20 years old now. So spending a few more years in school to get a PhD is a great long-term investment. So congratulations on that decision. I think that's going to pay off well. In terms of topic, I think artificial intelligence, machine learning is starting to pay off. I would certainly at least learn about that while you're a student and grad student, so that you're as familiar with machine learning as maybe I am with compilers and things. I think it's a fundamental and kind of transformative technology. I'm excited about what I work on. I think this, John Hennessy and I called this a golden age for computer architecture. Computers, the first word in machine learning is machine, so we need faster machines to make advanced machine learning. You've seen maybe some results about these very large models, like GPT-3 or Mina at Berkeley, where they do these amazing natural language processing. Those take really big, expensive machines. For those to be practical, for us to be able to use them, we're going to need advances in hardware to be able to make those things run much faster, much less energy, much more energy efficient. So I think there's lots of exciting areas. Great time to go to grad school.
Oh, that's most inspiring, Professor Patterson. Thanks so much for sharing with us your journey over the last few decades, and actually a very impactful journey has impacted all of us. So thank you so much, and I'm sure the audience were most excited to hear from you, and I thank you on behalf of all of them. Thank you so much, David.
All right, thank you. Bye-bye.